2.0. In the human-robot interaction task, pour liquor while following human order, HEX demonstrates flexible full-body control, quickly switching between glasses and accurately pouring into the designated one. In short, HEX shows that effective humanoid manipulation requires more than semantic understanding alone. It requires explicit modeling of the robot's body, its future dynamics, and how all body parts work together. That is HEX, a step toward humanoid robots that do not just understand tasks, but can complete them with coordinated whole-body intelligence.
Well, this is the first spotlight session, and the second is Sparse Video Nav. Yeah. Hello everyone, I'm Haizhang, and today I'm glad to be here to present our work, Sparse Video Nav. Regarding the whole body intelligence, while current research heavily focused on the manipulation tasks, the long-term stability of navigation with human-centric instructions remains overlooked. For instance, given a language prompt, a manipulation task operates within a nearly static background, whereas navigation involves drastic environmental changes. Maybe you can see these two following videos. Consequently, for instructions like the fetch me an object, the target often only appears at the very end of a video sequence. This causes severe supervision failure in existing VRA-based VRN algorithms, which typically rely on a short horizon of continuous actions. And simply extending the action horizon would also fail, as the following actions quickly surpass the view of the current frame, leading to the training collapse. Then, what would happen for the VRA-based vision language navigation algorithms when deployment? Due to the short horizon issue, this algorithm would fall in unexpected turning and dead-end tracking. We mitigate this issue by using the video generation model as our pre-training backbone, utilizing video generation to construct the supervision tailored for the long-term goals. To further extend the supervision horizon, we strategically find that using the sparse feature and the supervision can be highly effective, as it can simultaneously reduce the computational overhead. And this is our training architecture and the four-stage training pipeline with the sparse feature and the supervision or input for the training stages. And we choose to use the 2.1 with the 1.3 billion parameters. And this model only has the text-to-video model. So the first step is to adapting this to the video model, to the image-to-video model. And then we want to inject the history information effectively. So we use the Q former and video former to capture the dynamic information and the spatial information respectively, then can be utilized to compress the history information very effectively. And we then scale the whole model to achieve almost 10 times deployment acceleration. Finally, we use the inverse dynamic kind approach to learn the action outputs. And for the training data, we first find that if we only use the simulation data with 100%, the model cannot adapt to the real world. However, the current real world data sets are almost distorted and are length of language labels. Hence, we collect the data by ourselves and use some functions with the action camera to improve the stability. And currently, this is the largest real-world VLN data, and we have open sourced it to stimulate the iteration of the new VLN algorithms. And we test our method with a zero-shot manner in the real world. Even in challenging night case, our method has a good success rate. And this is also the first time for an entry manner method to achieve this. This is a very good achievement especially in this mountain atmosphere. Yeah. And please feel free to scan this QR code to download the dataset and maybe follow our method. Thank you. And the third is the human to any. Oh, let me see. Yeah.
Hi everyone, thanks for coming. Today I will present Human to Any, our work on human-to-robot transfers through constraint-aware computational planning. The motivation is that real robot data is expensive to collect and often tied to one robot, one setup, and one task distribution. In contrast, human videos are much more scalable and cover diverse objects and environments, but the challenge is that we cannot directly use human motion to train robots, because humans and robots have very different embodiments. There are two key challenges. First, the robot has its own kinematic and morphological constraints, so a motion that is nature for a human hand may not be feasible for a robot. Second, at test time, the robot also needs to handle scene constraints, such as novel object layouts, object combinations, and collisions. Our key insight is that the most transferable signal in human demonstrations is not the human motion itself, but the object-object interaction motion. For example, in pooling, what matters is how the container moves relative to the bowl. In mark hunting, what matters is how the mark approaches and aligns with the mark tree. This object-centric interaction is much less tied to the human embodiment. And based on this insight, human-to-any learns transferable interaction priors from human videos and learns embodiment-specific grasp priors from simulation, and composes them with test time constraints. Our method uses a factor graph representation to decompose manipulation into reusable interaction factors. This lets us learn different parts of the problem with different data sources. The object-object interaction factor comes from human videos, while the robot-object grasp factor comes from simulation. To process human data, we convert human demonstrations into object-centric interaction trajectories. Instead of imitating the human hand, we extract how the tool object moves relative to the target object. This gives us a more embodiment-agnostic representation for learning task motion. We then learn two diffusion priors, an object interaction prior from human data, and an end-effector grasp prior from simulation. At test time, we compose these priors using diffusion steering with particle filtering. This allows us to effectively guide samples towards combinations that satisfy task, grasp, kinematic, collision, and scene constraints. We validate the approach on multiple robot platforms, demonstrating that the learned interaction priors can be grounded across different embodiments and scenarios. For pull-in-bowl task, the robot adapts the pooling interactions based on the scene layouts and the surrounding environments to avoid collisions. For hard mark tree task, the robot needs precise alignment between the mark and the tree while avoiding the collision with the surrounding environment. In sort utensils tasks, the robot handles fine-grained placement in cluttered scenes, while also need to train up skills to reach long-term objectives. Across these tasks, the method transfers the object-level interaction structure rather than directly copying human motion. We also test cross-embodiment transfer on a different robot platform, including tasks such as pulling and using a roller. Since the interaction prior is object-centric, it can be reused across robot embodiments, while the grasp and the feasibility constraints adapt to each robot. In simulation, we further evaluate on diverse benchmarks involving fine-grained object interactions, pick and place, and long-horizon skill training. Quantitatively, human-to-any improves task-level throughput and also benefits from more interaction motion training data, showing that scalable human data can improve robot learning when represented properly. So to summarize, human-to-any transfers human demonstrations to robots by focusing on object-object interaction motion. We learn interaction priors from human videos, grasp priors from simulation, and compose them with test time constraints to generate feasible robot behaviors. Thank you, and please check out our website for more videos and details.
And welcome the fourth paper, Can we tune humanoid behavior foundation model for dynamic and context-rich tests?
Hi, good morning, everyone. I'm Mengjie Zhao, and today I'm excited to present our work named Can we tune humanoid behavior foundation models for dynamic and context-rich tasks? And this is a joint effort of my fantastic colleagues. Okay, recently, humanoid behavior foundation models, or BFMs, have emerged as a powerful low-level execution controller for whole-body tasks. They are trained on massive motion data and excel at generalized motion tracking, but they hit a bottleneck in specialized downstream tasks. First, their task-agnostic training targets average the tracking quality, which lacks the fine precision in contact force regularization and other requirements for complex interactions. And secondly, existing BFMs are mostly perception light. They are closed loop with respect to the robot perception, but often open loop with respect to the external environment geometry or task semantics. And consequently, a robot might track a reference motion perfectly, but still miss some object or fail to maintain some stable contact. And this brings us to our core question: can we tune the humanoid behavior foundation models for dynamic and context-rich tasks? And answer is SONA, semantic object-aware neural adaptation with residues. Instead of fully fine-tuning the massive foundation models, which is computationally costly and risks a catastrophic forgetting, we freeze the best BFM. And then we introduce a lightweight plug-in residue module. It predicts an additive residue action and add it to the original best action from the behavior foundation models. This ensures that the best model remains responsible for global balance while the residue handles task-specific corrections. And to enable reactive corrections, SONA injects the closed-loop semantic spatial observations directly into the low-level execution. We add the depth images from the two onboard cameras to capture the near-field geometry. And more importantly, to let the controller know which object matters, we introduce a dynamic object of interest mask. In real-world deployment, an open vocabulary detector, here we use the grounding signal, initialize the target from the task prompt, and then a high-frequency tracker. Here is Siam RPN++, updates the bounding box at the camera rate. And then combined with depth clustering, this provides some dense and temporary real-time semantic pointers straight to the low-level loop. And here's the overall framework. We froze the best BFM. Here we use the sonic and process the motion reference to extract the rich motion latents. And then Sona takes these latents, combines them with the robot perception, object mask, and depth image. Visual CNN and MLP fuse these features to output the high-frequency residual joint commands. This allows the robot to adjust its posture and bodies based on the immediate visual shifts, avoiding some slower high-level planning delays. Training such a residual policy effectively requires some structured pipeline. We propose three key strategies. The first is reference motion augmentation. To get the more reference motion besides some one or two certain clips, we introduce the motion augmentation pipeline. We fix the whole body context structure, but sample some varied manipulation targets using the inverse schematics. And this creates some rich motion variations locally. And then secondly, with respect to reinforcement learning, we optimize a composite reward function, balances the motion tracking, smoothness regularization, and also a unified contact reward pipeline. The pipeline includes first reference motion preprocessing to detect the contact points, and then adds the unified contact reward in training. And also, especially for the dynamic interaction task, we introduce some task-specific reward for it. And thirdly, for the dynamic interaction task, we introduce a teacher-student auxiliary loss. That is, a privileged teacher policy get the ground truth reference motion to track a drifted object. And this action provides some dense imitation signal for the actual residual policy that it trained. This drastically improves the sample efficiency of our student policy. And then we evaluated our sonar against the baseline sonic tracker across 3 challenging task groups. The first is contact reach task, which include table leaning, that is, you lean on the table with your weight least on it, and then also bed climbing, that is, you climb onto the bed in a standing pose, which includes the weight transfer. And the second is dynamic interaction task, which is stand reach. And the third is a combined task, that is, you lean on the table while reaching a moving object. And in simulation, the evaluations shows that for the contact reach task, our sonar policy dramatically increase both the contact rate and also the energy assumption reward. That is, it learns to maintain the stable contact while also learns to lease its weight so that it could reduce energy. And instead, the sonic policy will also keep itself in the air while trying to conquer the gravity using its own energy, which is revealed by the high energy consumption. And also on the dynamic interaction task, our policy reveals some the end effector tracking accuracy with respect to a moving object when the reference motion is actually fixed. And here is the real-world deployment. Yeah, for dynamic reaching, as you can see, the first is reach while standing and also reach while leaning. To notice that the reference motion here is actually not moving, so it is adapting by itself. The third, then it is the bed leaning task, and here is the bed climbing. Yes, as you can see, the left is our sonar policy and the right is sonic. It failed to make such weight transfer and then it failed. Okay, thank you for listening to my presentation, and our work is actually still ongoing, and we will further refine it, and I will expect any further discussing. Thank you so much.
And for the next one, the native memory compression for long horizon robotic manipulation.
Hello everyone, I'm Ziyi. Today I will present native mem, our approach to long horizon robotic manipulation. This idea is simple: compress every historical frame into one token and make a trained VLA can read it directly. This gives a dense minutes level memory without an external planner or memory module. So why does memory matters? In the routine skills, the current image may be enough, but in the long horizon task, the same image can require a different action depending on what happened before. An item may already been scanned. A field grasp must be retried. The policy must distinguish an attempted but not succeed action from the whole process. So the visual history grows as the historic horizon T times update frequency N and times M tokens per frame. So the dense long horizon history quickly becomes expensive and unfeasible. Keyframes or summary can miss brief failures, and external features may be unreadable by the VLA. Native map set M to 1 and append these tokens to the normal input, retain more than 160 history observations without external module. So the training has two stages. In stage one, a learnable query puts each frame view into a token into the VLA's own visual space. We freeze the pre-trained VLA and train only the memory branch. We use no image reconstruction keyframe. We only use the original action loss. Because the policy is frozen, the tokenizer must present the history in a form that the VLA already understands, and keep only the information that improves the next actions. And in the stage two, we cache the memory tokens for each demonstrations, then fine-tune the whole VLA with the current observation, task prompt, and history. At the deployment, the tokenizer continuously updates a compact queue, while the policy reads when predicting actions. With 100 real robotic trajectories and about 5 hours fine-tuning, a single frame VLA gains the long-horizon memory. And the results shows with the native memory compression, we can improve the success rate from the 84% in the simulation and 98% in the real-world robotic. And our method also have a high data efficiency. We use only 10 demonstrations can match or exceed baseline trained with 50. And here are some cases we show that what the memory is actually doing. So the attention visualization makes the token interpretable. Especially the memory query focuses on the manipulated object gripper and the task relevant regions. And you can see in the class button, a click button task, it focuses on the buttons. And here they must put the block into the middle and put it back to the original location. So you can see the attention focus on the queue. And temporarily, the VLA retrieves the key event. It not simply keeps the newest frame. For example, in the click button task, it focuses on the 3 stages, and in each stage it clicks the specific button. And in the other task, it focuses on the cube's original locations. So the action supervision teach what is worth remembering. And here is an interesting case, the failure recovery. So in this case, the third item grabs failed and then succeed on the retry. So the robots have made 4 attempts but completed only 3. So if we by action counting, it would stop at here, but the visual memory capture each outcome. When the first item appears, the policy realizes it is unscanned and continuous. So this recovery and retreat pattern was absent from the task-specific data. And so the memory reactive the pre-trained VLA's general capability. And here are some takeaways. So we need to keep long horizon memory dense and make it native to the pre-trained policy. So we can use the action supervision to retain only decision relevant history. And finally, the memory supplies the right historical context, and the pre-trained VLA supplies the skill. You can also scan the QR codes for more detail and our key ideas. So that's all. Thank you.
Okay, okay.
So, hello everyone. My name is Anxin. I'm excited to present our work, visibility aware mobile grasping in dynamic environments. Okay. So mobile manipulators often work in spaces where they cannot fully observe. We consider scenario where robot's camera observe only a limited region. So this point cloud represents the scan area and where the rest remains unknown for the robot. So robot may also have only rough estimates of where the target object is. So it must jointly decide how to move and where to look during the mobile manipulation. This leads to our central question. How can a mobile manipulator safely grasp in dynamic unknown environments under limited visibility? Ignoring uncertainty and limited visibility, mobile manipulation can be formulated as sampling variables in this constraint graph. The goal is to jointly sample a whole body trajectory, goal configuration, and grasp pose that satisfy collision avoidance, motion, IK, and grasping constraints. Hierarchical sampling optional combined with learned sampler enable real-time planning to form the foundation of our approach. As mentioned earlier, the maintained map and estimated target pose are only partial observations of the true environmental geometry and object pose. So ignoring this partial observability may cause the robot to collide with unseen obstacles or occlude the target object by itself. In this work, we consider two additional constraints, the collision visibility and the target object visibility. We developed a practical mobile grasping system that simplified original constraint satisfaction problem for real-time planning while remaining the ability to deal with the limited visibility. Our system closes the loop among three components. The subgoal policy begins with a rough target estimate, and if the target is visible, it samples grasping variable while keeping the base fixed. If fails, it samples whole body variables. This hierarchy enables progress while gathering information needed for grasping. So the active perception policy directs the camera towards task-relevant and safety-critical regions. Each observation updates the maps and allowing the robot to focus on the area needed for its future action. The motion planner converts selected subgoal into whole body trajectory. Here we modify WAMP to be able to solve non-holonomic whole body motion planning. In simulation, we randomly place objects in diverse environments, removing unreachable cases and evaluate the final grasping outcomes. Any collision with the environment is considered as a failure. And the result in simulation shows our system achieve reasonable success rate. Remember, this is a random generate target pose in an environment that the robot have never seen before. We deploy the same pipeline in a real fetch robot, demonstrating visibility mobile grasping beyond simulation with imperfect sensors and noisy localization. And we deploy our system in an online robot mesh platform, which you can try in the poster section. The interface provides robot camera view and the goal specification. During execution, you can see the robot continuously replan the whole body motion while considering the potential collision with the unobserved region. And when robot finds the chair block its base pose from reaching the table, the robot automatically adjusts the base target and the whole body configuration. And finally, it re-estimates the object pose and complete the grasp.